Hi guys, welcome to the seventh lecture on model-driven engineering and model-assisted software development. So the previous lecture we were discussing the integration of model-driven engineering with the software development process. Let's just double check we're recording. It's all right. So what we meant by that was that there is the body of knowledge of model-driven engineering, and you can apply it in isolation, but in practice, when you try to make use of it in the real world, you're going to have to integrate it with what precedes it and the surrounding environment. We already had discussed the difficulties in knowing where the body of knowledge begins and where it ends, and all of these are very subjective notions, really. But it is clear that things such as agile and the software development methodology itself and other items are actually not directly related to model-driven engineering. They're not part of the body of knowledge. So we discussed the different ways in which we can integrate it, such as the dual track approach. We also mentioned the difficulties with the dual track approach, where the key thing is to try to get to this mythical what was the word I used? Good enough generalization. There we are. Barely general enough. And the idea with the barely general enough is that when we integrate, because we have to have two tracks to develop the model-driven engineering component of a project, we need some kind of generalization on the system. Otherwise, we end up creating something that is completely hard-coded for a given application. But we don't really want too much generalization. Otherwise, we end up creating a super complex application that is unsuitable for any specific application because it's a superset of all possible functionality on a given problem domain. In order to target, well, once we enter the world of generalization, we need the language required to talk about generalization in configuration, and that's where we enter variability. So the point of these chapters has been to introduce the domain of model-driven engineering. In other words, the vocabulary, the basic concepts required to understand what it is that people are trying to do with model-driven engineering. And this is the last chapter on my notes. Now, I don't want to say by this that we've covered the whole of model-driven engineering, nor that we've covered in any significant depth. What we've done instead is we just we created a very simple or thin amount of knowledge that enables us to then make sense of all these concepts together when we start talking about model-assisted software development. This is not an extensive or exhaustive coverage of any of these terms, and really, in order to understand these terms, you really have to play with them for a while. It has taken me a very long time to even understand the basics of this. I think until you start excuse me, until you start creating your own DSL, until you start playing around with tools such as EMF and other tools for model-driven engineering, it's very difficult to get a very good understanding of what it is that these things do. I don't think it's necessary for you to do any of that in order to understand model-assisted software development. You just need to build up the vocabulary of all these terms, because we are going to turn MD into itself in sort of a recursive way, as we shall see later on in these lectures. What we're going to talk about today is the last bit of terminology that we need in order to introduce MASD. Of course, we're not going to strictly start by introducing MASD directly in the next lecture, because a thesis has to be organized in sort of a well-defined sequence. We first must review the state of the art. Then we start talking about the requirements, and then after the requirements, we propose our new approach. So in some ways, we're still going to have to recap some of this stuff once we start reviewing the thesis itself. However, this level of detail is too detailed for a thesis, and that's why I had to separate out the notes from the main document. But I do think that if you're a regular software engineer, you won't be able to make sense of any of the stuff that we're talking about in MASD unless you have this basic background, and that's why I've created the notes. So variability then. the key thing about variability is, as I mentioned in the previous lecture, we are used to talking about variability. It's just that we don't think of it in that way. So whenever you create a program, you are bound to create some set of options that enable you to configure that program. The most basic program, something like Dogen, for example, has at least a set of command line options that you use in order to determine what's enabled and what's not enabled. I mean, if I was just to switch over to, say, Emacs and open up a shell, and if I just go up to let's just have a quick look. Like I might even have, no, I don't have a version installed, so that's fine. So what we're going to do is we're just going to look at a binary of Dogen, which we probably have lying around somewhere, if I could find it. Build outputs, and here we have the different builds. I must say this dark blue is not the best choice of colors, because I can't really see very well. So if I just grab, say, this chap here, and if I just run, so as you can see here, Dogen provides you with a whole load of options that you've got. For example, you can determine where you want the output to go. You can determine whether you want logging or not, where would you want the logging to go, whether you want some tracing, what kind of reporting you like, whether you like diffing, and so on. So there's lots of options here. In addition, you have different modes in which you can execute the program. Now, as any software developer will tell you, this is not a novel thing, really. I mean, we've all been coding for a very long time. We all know what we mean by command line arguments, and we all know what we mean by a configuration file, such as an ini file in the Windows world, or the .conf file, perhaps on Linux. We also know about maybe database configuration. In a sort of a microservices world, you probably know about console and some other form of distributed source of configuration, and so on, right? So none of this is novel, really. What's novel about MD, and when I say novel, of course, this is all 20, 30 years old, but I mean novel from a perspective of a regular software engineering, is that MD actually spends some time reflecting on what it means to be configurable. Again, it is important to understand when I say there's a lot of history rewriting that I'm doing in these lectures. When I say MDE, it gives you the impression that all this analysis that was done in the realm of variability was done under the MD umbrella. Actually, the world didn't really, the history didn't really work that way. What happens was some people have done, lots of different people under lots of different contexts have done research on variability, and then MD absorbed that as part of the body of knowledge. A lot of this work precedes the existence of MD, and in effect, if you were to look into the history of program families of programs, you'd see Dijkstra, as early as the 70s, was already talking about program families. So this is all very old sort of stuff. And it's not really something that was invented by MD. But the way the MD body of knowledge works, it absorbs this knowledge because it is related to the objects of model-driven engineering. So therefore, we consider it to be part of the canon of MD. So when I say that this is invented in the context of MD, you understand what I mean. I don't really mean in a historical way that MD was the reason why all these things were invented. More the other way around, that MD absorbed this knowledge because it makes sense in terms of what it is that we're trying to do with MD. So we're given that caveat. I'll continue with my explanation. So MD spent a lot of time analyzing or variability, what it is, what does it mean to allow configuration of program, and the logical consequence of that, as Dijkstra already said, is really what we're trying to do. Really, is we're trying to create a family of programs. So these programs are related, but there is some distinctive characteristics of each instance of this program. In other words, you can imagine that when you instantiate Dogen with a certain set of configuration options, you have a certain instance of the program, and when instantiated with a different set of configuration options, we have another instance of the program. Of course, we don't think about it that way because it's the same binary. But if you were to try to abstract yourself from how the configuration is done, whether it's the runtime configuration or is it the compile time configuration, and so on. Really, conceptually, what you're trying to do really is you're trying to say that there is a notion of instantiating a program with different configurations. And you can think of that abstract, higher level concept of the program that supports all possible configurations as sort of the template for the program. I'm going to use terms that are not really variability terms, just so we can bridge the gap between normal software engineering and model-driven engineering. So if you can think of that as the root of the family or the template of the family, and you can imagine that each instance of the family is a specific configuration that you apply. And there's this set of possible configurations that you can create, which could be quite large because you can, as you can imagine, the root could be really flexible. It could allow lots of flexibility. Um, so why would this be useful? Well, this would be useful not so much when you're talking about simple things such as the command line configuration or even a config file, but more like when you think of um, when you start to take this notion and abstract it further, especially in the context of model-driven engineering, you can imagine that you could create one single domain architecture for a group, for a family of programs, and you can then instantiate that architecture differently depending on the specific application. So, if you recall in the previous lecture, we spoke a little bit about the domain architecture development thread, which is basically the set of infrastructure that we create, the basic language that enables you to then talk about the application that you like to instantiate, and the application development thread, which is that the real programs that we're going to create for users to use. So let's just use some more concrete examples because the problem with these things is that it becomes so abstract that it's difficult to reason about it. So let's imagine you've got a set of microservices and you'd like to create, say, 5 different microservices. Because I'm familiar with the domain of finance, I'll give examples from that domain because it's easier for me. So let's imagine you need a booking service. Let's imagine you need a market data service and so on. And all of these services are very different from a domain perspective. But if you think about it in abstract terms, they will all have a lot of similarities. They will probably all have some kind of communication mechanism. Maybe they'll communicate over HTTP. They'll probably all have to do some kind of logging. There'll be lots of infrastructure that will be common to all these services. And also, because they are part of the domain of finance, they probably will share a set of domain objects that they will communicate with or communicate via. And so you can imagine the domain architecture will be the abstraction of all these commonalities into um, something that is then flexible enough to describe all of the services that you're going to instantiate. And each service then becomes an instance or an application of the domain architecture. Variability is what describes what is configurable in the domain architecture. So, for instance, if you'd like, say, no logging in the booking service, but you need logging in the market data service, for example, variability will enable you to determine that option of the service is configurable as an option, in fact, and it enables you to express whether you want to switch that on or off. Now, logging is not a good example because normally you would switch on logging on or off via configuration. But you can imagine that there's many other things, such as, for example, let's say that you would like some services to communicate over RabbitMQ or some other message queue, but other services to only communicate via HTTP. Now, you don't really want, most likely, I'm not. None of this is black and white. This isn't a thing that's very important. There is no such thing as you can't or you must not, or all these things are options that you must think about, you must reason about in terms of a given application. So in this particular case, when I say you don't want to, I mean, let's just say that for the particular example, you do not want to. But it's not nice to say that you these things are set in stone in any way. So going back to my example, say you one service you want that service to only communicate via RabbitMQ. So in other words, you don't want to have any code in that service that enables you to communicate via HTTP. Now, this is a bit different from having a configuration option. In this particular case, we're saying that when you instantiate that particular application, you don't want any functionality to be present in the source code, so that you can't even configure it to run HTTP, to listen on HTTP, because there is no code for HTTP. So that's what we're trying to aim at when we talk about the abstraction of variability and product lines. The product line is basically described by the domain architecture, and the instantiation of the product line is is the domain of that instantiation is given by the variability. In other words, what options are available is your variability. So hopefully that makes sense. And then so as soon as you introduce variability and as soon as you start to increase the scope of variability, it becomes quite pressing to have some form of variability management. Because you start off with something really simple, such as the example I gave, and then you will increase variability quite a lot. I mean, if you take Dogen as an example, we have a lot of the scope of variability is huge in Dogen. There's a lot of things that are configurable. We will discuss that later on. And so it's very important for us to have some kind of way of managing the variability. Else, it becomes just like any other program with lots of bits of code with ifs and else and so on. One interesting point that we should probably make here is this: we discussed a little bit about domain engineering, and so as we mentioned before, the separation between domain engineering. So as you can see here, what's happening with domain engineering is we are trying to offer more and more variability within domain engineering. Um, the idea is that you start off perhaps with a very limited number of options as you start to evaluate the domain. But over time, you're going to figure out that there's lots and lots of knobs in your application that are required. And as you find those knobs, you introduce those knobs into the domain architecture. However, when you are doing the application engineering, your job is the opposite job. Your job is to take away variability. Because really, a given application, a given instance of the domain architecture should not be infinitely variable. I mean, you've got a specific requirement. You're writing a booking service, for example. The idea should really be that you've got the smallest possible amount of options available to show to users. And really, as you instantiate that particular application, what you are doing is you're narrowing down variability, you're constraining variability to that specific application. So there's this interesting dichotomy between domain engineering and application engineering, which I think is quite interesting. And as I said, it's very important to understand that we've always had variability management. We were just not aware of it. And as usual with model-driven engineering, what we're trying to do is we're trying to abstract ourselves on the software engineering process. We're trying to reflect on what it is that we're doing. And by doing that, we're trying to make things that are implicit explicit. And why would you want to do that? Well, that's a very good question, actually, because you may think, well, I've been using config files all along. Why do I even need to know about variability? Well, the literature identifies a few reasons why you want to be aware of variability and you want to separate that from typical software engineering. First is variability abstraction. Because we don't tend to model variability, we tend to bundle it with other things, such as, for example, domain objects. Now, some of you may say, well, in my code, I always have a namespace for all my configuration options, and I keep them separate from, say, domain types. So, I don't know, I'll have an object for my command line options, which is completely separate from the domain objects. And we do that in Dogen as well. What we mean is a higher level of abstraction of that idea. It is the same idea that we want to separate the objects in the domain that are related to variability, but we want to do that at the higher level. So when you think about the architecture, you're already thinking about variability. So you want to at all times during the development process, you want to be aware when it is that you're doing some domain modeling versus when it is that you're doing some variability modeling. And you want to make sure you understand when you're doing one and the other so that your architecture, your domain architecture reflects those two concepts separately. In other words, one thing is to model a domain object, and the other thing is to describe what's variable about that domain object. Sorry, just one second. I can hear some weird noises. This house is not exactly conductive to thinking. So as I was saying, it is important to, at all times when you're doing modeling, to keep in mind what kind of modeling you're doing. And by having this abstraction, it enables you to think of variability independently of the implementation mechanisms. So this is very helpful when you think of a domain engineering because Well, one way of thinking about it is, if you can imagine, you've got two, say you're thinking about a domain. So, for example, let's go back to finance. And maybe you're thinking about, say, an option, which is a financial instrument. And maybe what variability enables you to think about is enables you to think about it as, um, what's configurable about that option. So what is a fundamental property of an option, and what is actually a configurable aspect of the option. And what that means is that maybe you're going to have different kinds of programs or different kinds of applications within your architecture, within your family of programs. And some of them may need some aspects of the option, and some of them may need other aspects. And these aspects will be configurable. So by having in mind the concept of variability, you will try to separate the modeling of the domain objects from the modeling of its variability, which is very important. Of course, then there is the notion of documentation. So the fact that you are separating and modeling variability aspects. Let's double check we are recording. Yeah, we are. The fact you're separating the variability aspects means that you're actually documenting them, and you are making the ubiquitous language of the domain much more explicit with regards to variability. So when a user or a developer is trying to make use of the domain architecture, the developer will be able to just refer to the variability entities in the domain architecture, and will know what they allow you to do or not. In a way, that becomes a variability language, which makes it much more obvious what it is they're trying to do. The third point, which is also very useful, is traceability. When you enable or disable knobs, in general, you have you can imagine the surface, or the if you think of it in terms of a combinatorial explosion, um, the more knobs you add to a program, the more possible permutations you're going to have in that program. And a very common problem is, how do you then test and validate all the possible permutations? Now, of course, you can't, because, as you can imagine, as this number of knobs increases, the permutations increase quite rapidly. So the best thing you can do is empirically try to figure out if everything's working correctly. Not everything, but a subset of things are working correctly. And for that, you need traceability. So you need to know what's on and what's off. And when it's on, you need to make sure that there is some kind of logging or some mechanism that enables you to determine what's happening with that particular feature. So the awareness of variability improves variability traceability, because you have to explicitly have to switch on those options, and possibly you would also have some kind of tracing and logging related to that feature. These are things to keep in mind when you're trying to separate variability management from variability modeling from normal modeling. Um, Unfortunately, because variability is very useful, at least in terms of the literature, a lot of things have happened in this space, and there's lots and lots of different notations, modeling languages, and so on. I'll name a few here: and/or tables, decision models, OVM. I mean, there's CVL. There's many of these. Um, we don't really need any of these languages for MASD as such, because we make use of variability in a very simplistic way. But I think it's useful to look into one of these languages, because the languages are an instance of the variability domain, and as such, they enable you to see um, all the entities that belong to this domain. So before you model these entities, you should really know what they are. So that's why we decided to look into one of these. And we just decided, because it's very popular, we decided to look into feature modeling. So feature modeling originated on this feature-oriented domain analysis, which is a fairly funny acronym in Portuguese. And it has been extended by quite a few researchers in the literature. I just took one of these variants because, funnily enough, this is relates to variability, but there's quite a lot of variants of this particular language. We just chose one variant because it seems popular enough. And to be honest, it doesn't really particularly matter. We just need something that is comprehensive enough in the domain of variability to enable us to identify the entities of this domain. And this is suitable for what we need. Um, so the notion of feature modeling, the key notion in feature modeling is, as you can imagine, features. Um, as usual with model-driven engineering, there is no strict definition of what a feature is. We go back to this W2 world, this Wittgensteinian language game sort of way of looking at the world. A feature, according to Groher and Volta, products usually differ by the set of features they include in order to fulfill customer requirements. A feature is defined as an increment in functionality provided by one or more members of the product line. So as you can see, what they've done is a bit of a cop-out, really. What they've done is they've redefined, or they defined the notion of a feature from the notion of a product family. So if you don't know what a product family is, then it becomes a little bit recursive, really. But what they're trying to say is, if you think of this in a sort of more mathematical way, you can imagine that you are taking a number of instances and you're trying to abstract commonalities of these number of instances. A little bit like you come up with a base class by looking at different instances of the descendants of the base class. Not that I'm saying this is a good idea, but I'm just using this as an example. So perhaps you could say, well, look at a cat and a mouse and some other animals, and perhaps you could say that there's a base class called mammal, and maybe if you introduce maybe a lobster, then you would say there's a base class called animal, for example. A bit of a random example. But this is kind of more or less what we're trying to do here with the product family. You're basically looking at a set of products, and then you're saying that, well, these products have got a set of features, and then you look into the product being an application, an instance, and then you say, well, I can see there's 5 or 6 features that are common, or a feature is common to several of these applications. So therefore, I isolate this as a feature, and I'll create this concept at a higher level construct, as a higher level construct. So once you accept this definition of features, we can think of a feature as a cohesive unit of functionality with distinguishable characteristics relevant to a stakeholder. And of course, now we introduce another problem, which is once you've isolated features, just like once you isolate objects, the interplay between features is a major source of variability. Because of course, let's say you have a feature F1 maybe, and maybe switching on feature F1 requires feature F2 and F3 to also be switched on. Maybe switching on F1 means you can't switch on F4. So now you have to have this language to describe the relationships between features, and that itself is a source of variability. Now that we've defined features, we can now move over to the second concept in the feature models, modeling, which is feature diagrams. So feature diagrams in feature models, these are basically ways of describing variability. So you can imagine that we normally use YAML to describe class diagrams and other structural entities. The feature diagram is akin to a class diagram, I guess, in the sense that you're using it to describe the set of features that exist within a software system. And the feature model is in effect the feature diagram plus some other information. The problem with the feature diagram is, as it is designed in this language, it is not comprehensive enough to express all information required in order to model the features. For example, the feature descriptions, the binding times, how the features bind, the priorities, and other sort of related information. That's not part of the language, the base language. So the feature diagrams then require some additional information, and to distinguish between the two, we'll call the feature models. This enriched version of the feature diagram. So let's have a look at the entities that are part of this language. So here we got a feature, and there's a cardinality that associates this feature. So this feature has got a cardinality of 1, so it must be on. This feature, because the circle is, in this case, the circle is filled. In this case, the circle is not filled. So when the circle is not filled, the cardinality is 0 and 1, which means optional. And then there's the possibility of having a cardinality NM, which is this case here, where there's no circle anymore. And then we can also define grouped features, and there are other elements of the language. Now, I don't want to dwell too much on this. I'm just going to show you an example of a diagram. So in this diagram, we're trying to describe an imaginary car, and we're trying to think of the features that the car has. So we have a body, an engine, and the engine can be electric or it can be gas. You can have a gearbox, which could be manual or automatic. It may require a key or not. It may have a license plate and so on. And so, as you can imagine here, what we're trying to do is we're trying to create a domain architecture for some imaginary car factory that allows you to configure a car to create a product line. So let's take, say, for example, a Tesla. You can imagine that you could say there's a Model 3 which would have a set of specific options, and then even in that specific set of specific options that distinguish between, say, a Model X and Model 3, you would still have perhaps a Model 3 new versus Model 3 old. So, for instance, maybe this is a single body or a cast version of the Model 3 versus the older version of Model 3. So the idea here is that the domain architecture is giving you the language to describe all the different variations of a specific application at given instance of Model 3. But not that when we say an instance, we don't mean an instance as in an actual Model 3. We're talking about the production line that makes Model 3s. So if I go back, this becomes a bit more obvious if I go back to here. So what we're saying here at the moment is the meta model contains a language that enables you to describe the variation that exists in the model. And so this is akin to a factory. And then that factory then generates instances of those objects. So this guy here contains the language needed to describe all the possible permutations of, say, Tesla cars, including Model X's, Model 3s, and so on, as well as the specific configuration between different kinds of Model 3s, like the Model 3 made in Berlin versus the Model 3 made in Silicon, whatever it is, the factory is in somewhere in California, versus the one made in Texas. These are different Model 3s. Perhaps the battery pack is different and so on. But when you instantiate this, you don't actually instantiate the Model 3, you instantiate the Model 3 factory. And then from there, you start to produce actual Model 3s, right? So this is how you model that domain from a variability perspective. So this diagram is describing the permutations that you can have in this context. Now, of course, you probably already noticed that this diagram does not look at all like a UML diagram, which is a bit of a problem because, of course, you are assuming you are using some form of modeling such as UML. You are probably going to be modeling these entities in UML. That means that you would going to end up with a feature model somewhere and a class diagram somewhere, a class diagram somewhere. And now you have a problem of saying, well, how does the class diagram relate to the feature diagram? And that's a problem. If you were not to do anything with it, and you were just to basically create this as a way to for your team to talk about features, I mean, it's still useful, just like a class diagram in a napkin is still useful, or say a plant UML diagram is useful for your team to discuss things. But it's not really model-driven engineering because you're just going to throw that away at some point. Ideally, what you really want is some kind of mapping, some kind of automated mapping between the feature diagram and the class diagram. And so the literature spends a lot of time thinking, how can we integrate feature models with other kinds of models? And I was particularly interested in the work of Groher and Volta because they spend some time discussing the taxonomy of variability. They spend a lot of time thinking about the taxonomy of variability. Now, why would you think about the taxonomy of variability? Well, because in order to integrate variability with class diagrams and other types of normal models, you need to understand variability quite well. And that's why the taxonomy is important. So in their description of variability, they've basically decided to divide variability into two kinds: structural and non-structural. Structural variability is more related to the DSL itself. So this is where I think model-driven engineering becomes really, really complicated. In a way, the programming language is actually a form of variability, if you think about it. I mean, the fact that you are programming in a language, it gives you infinite variability because you can do whatever you like. So a bit like the discussion we had a few lectures ago. is a programming language a modeling language or not? Actually, these are all W2 terms, and because it's a language game, we can say whatever it like. And I think we probably would almost any conclusion can be reasoned about, and you can provide justification for one choice or another. I try to justify that there is a reason why you should distinguish between programming languages and modeling languages, because in my view, and I think it's a view shared by a lot of model-driven engineering people, um, it is all to do with abstraction. The idea of modeling language is when you're trying to raise the abstraction level and you're trying to get closer to the domain. That's when you're modeling. And when you're lower, when you're closer to the machine, you're programming. That's how we justify the need for this distinction between modeling versus programming. Because of course programming is modeling, so it's But similar with variability, you can make an argument which would not be unreasonable that programming is variability modeling, because of course your program will contain the programming language gives you the ability to model variability, right? But what they try to say then is that there are two types of variability. There's this notion of structural variability, which is closer to programming as variability, um, and non-structural variability is when you start making use of configuration languages. Um, so really, what we are more interested in is non-structural variability, and we should describe somewhere around here. Just trying to remind myself of what I wrote here. Yes. So they basically make these two distinctions. They make the distinction between structural and non-structural, which, as I said, is more to do with the DSL itself, and non-structural is more to do with a configuration language specifically made for variability. Um, and then there's the distinction between input variability and then generational variability, I believe. Yes. Um, and so the idea with the input variability is the input variability is on the model itself. So if you recall, we discussed the model cascading a few lectures ago, and the idea is that a model is an input, and then you apply transformation, and then you move that model to another representation. And so when we discuss input variability, we're talking about variability within the input model. I think maybe if I just go back to a diagram we had a few lectures ago, leave it around here somewhere. Problem space to solution space. That's it. So, as I mentioned before, in an ideal world, again, we are talking about all idealized representations of model-driven engineering rather than practical representations. But in an ideal world, there should be a requirements model, which then gets transformed into an analysis model, which then gets transformed into an architectural model, which then gets transformed into some component design sort of model, and eventually reaches source code. So, in this idealized world, from the input model would be the requirements model, which then gets transformed into the analysis model, and so on. And so, what we're trying to say when we talk about input variability is we're trying to say that the input model is, in a way, a form of variability. Um, and that input model contains two types of variability, structural and non structural. The structural variability of the input model is, if you think of it as a class diagram, is the classes it's themselves. Um, so so your structural diagram, the diagram representing the structures, the fact that you choose to put a set of attributes or the types of those attributes and so on, that is structural variability. Um, and non-structural variability is not directly related to the structure of that model, but is related to some kind of configuration language that exists next to the model, and that is configuring some aspects of your program, but not the structure itself. Now, you may think this may sound very confusing from a software engineering perspective. It took me a while to understand what they meant by this, but try to imagine that you're trying to instantiate a class, and this you just have to raise your abstraction level. You're at the meta model level here. You're trying to determine whether, for example, your option is going to appear with an attribute or not, and that's actually structural variability because you're instantiating that class with some attribute present or not. the thing that determines whether the attribute or not is present is some form of configuration. And you need a configuration language in order to do that. And that's where you enter the world of non-structural variability. So the non-structural variability is a configuration language that describes some set of options being on or off, and the structural variability is the actual structural diagram, say. And both of these things are input variability. And then you take this transform, and then you apply the transform, and then the transform will then get generated. Options related to the generation itself are, of course, going to be called generational variability. Now, I am not going to spend a lot of time talking about all these different aspects of variability, because in the end, as much as I spent time researching all of this, we ended up not using any of this for Dogen. They are interesting concepts, but they're very hard to explain. They're very low level, and I think I probably will just end up confusing things rather than making things clearer, which is the objective of these lectures. So I'll just cover one thing very quickly, which I think is important, which is positive versus negative variability, because we do use this in Dogen. So the notion of these are both types of input variability. The notion of positive variability is when you're trying to come up with a variance, and the idea of how the variant gets generated is you either start with a core that is always present, and then you have got a number of knobs that enable or disable things in addition to that core. That's when we're talking about positive variability. Negative variability starts the other way around. You basically you've got an overall model, sort of the superset of everything, and then you start to switch things on or off from that superset. Now, this is a very good example of this W2 dichotomy that I've expressed. These two terms are very similar, and in fact, to be honest, you could probably make a case to say that they are the same thing. It is. I think that just like with our barely general enough, I think also there's a point at which delving into the taxonomy of model-driven engineering starts to produce I wouldn't say negative returns, but at least diminishing returns. Um, One must have the ability to say at some point that one has found enough taxonomy, enough entities of the domain sufficient to model what it is that you're trying to model. And then at that point, you need to be able to say, well, I don't necessarily need to continue on this process of understanding the domain further. I understood enough to model, and now I can go and model and do more things. And then, if required, I can then go back. And that's more or less that's exactly what happened to us when we're trying to learn about the domain of variability. In fact, to be honest, about all of model-driven engineering. You can literally learn model-driven engineering forever because the body of knowledge is so vast and so extensive that there's loads and loads of concepts within it. But at some point, you understood enough to try to address a specific issue, and that is a classic. That's exactly what happened with us when we started to deal with variability, because the more we started looking into variability, the more we started to think that these concepts are so difficult to untangle from each other. They're so similar um, that unless you start to apply them in practice, it is very difficult to understand precisely what the concepts mean. Um, so once I moved away from positive and negative variability, which, as I say, we use that in Dogen, we mainly we made use of these concepts for two specific use cases: one for structural variability and the other one for non-structural variability. In other words, negative variability makes more sense for structural variability because you're just switching bits of a class on or off, but you define the whole class in one go. Whereas positive variability is more useful for templates because your template will have a core of the template present, and then you're going to switch bits of the template on or off. And this is the edges of the usefulness we found in practice, in an engineering sense, of these terms. But the more we started to go down this road, the more we started to see that a lot of these concepts are perhaps not as useful as you may think, unless you are on a very specific, specialized use case. And so at that point, I more or less put a pause on the research on variability, and I concluded that we knew enough to explain all of our use cases. And that also is the end of the notes. At least this was a bit of a rambling lecture, but to be honest, that's kind of the point, really. These concepts of the body of knowledge, they don't make a lot of sense in abstract terms. They only make sense when you start applying them. Um, these are the concepts that were arrived at in the MD body of knowledge are product of many, many years of people discussing lots and lots of instances and abstracting those ideas into a higher level concept. If you start by looking at the body of knowledge, you just see this abstraction. And by seeing this abstraction in um, without the context of the instances, it is very difficult to make sense of what it is that we're talking about. I'm hoping that now that I've introduced all the key entities of the domain, once we go back and start to see how these things work in practice in Dogen, they will make a lot more sense. Um, and what we'll do is we'll go backwards and forwards between these two between theory and practice in order to make sure that these things make sense. And this is the end of our series of lectures on the notes. I the point of the notes, like I said, is just to introduce all these concepts. So I don't think that they're going to make a lot of sense, but hopefully they make enough sense that the the thread of the argument is coming across, or what we're trying to introduce here with model-driven engineering. So I'll end this lecture now, and we'll start the thesis proper in the next set of lectures, which will require a bit more preparation because I can't actually use the thesis as visual material. I'm not sure if I'm allowed to do that before I present the thesis in the Viva. So I'll have to create a series of presentations in org mode to discuss those topics. But that's about it. Thanks very much for watching.